How's that? Better.
Experiment?
Nothing to do with me.
All right, I am going to get started. If that's okay, we ready to roll?
Yeah, absolutely.
It's my great pleasure to introduce David Wallace to all of you who already know him. So I don't have to say a whole bunch of stuff except that. We are really delighted to have him as a colleague in our department and in the philosophy department. He is the, what is your title? W.A. Mellon. There's lots of Mellons.
Yeah, keep track of the letters.
W.A. Mellon, Professor of Philosophy and Science, and a huge, wonderful colleague to have indeed. He writes about everything important in philosophy of physics, including emergence and quantum mechanics and multiverses and statistical mechanics. And so if you have any questions about anything to do with physics or philosophy of physics, he's your guy. I'll just mention his most recent book was Philosophy of Physics, a very short introduction with Oxford. And of course, he's very well known for the emergent multiverse quantum theory according to the Everett interpretation, also with Oxford from 2012. And with that, I'm going to turn it over to David.
Thank you. I would give some kind of apology for any sense in which this is a little hasty or unprepared. I was a certain amount of rush putting the final slides together. But then I remembered I kind of set the expectations here because the last time I did one of these talks, I turned up 20 minutes late and did it more or less from memory. So relative to that rather dismal start to my career at Pittsburgh, I hope this will be a model of careful preparation and advanced planning. Okay, structural realism starts with a very seductive idea. And the idea is something like that the categories for ontology and description of the world given by metaphysics and given by the more formal corners of epistemology slice the world too fine for modern science. So that the way we individuate theories requires us to draw distinctions narrow enough that physics doesn't care, that the way we consider changes from one theory to another has them changing radically in ways that physics doesn't care about, and that if we were to reconceptualize our idea about what a scientific or in particular a physics theory looks like, so as to focus attention on the structure of the theory, we would somehow dissolve a great many epistemological and metaphysical problems in our understanding of science. But it's proved frustratingly difficult to get precise on what that notion is. Attempts to actually develop an epistemic, or as was later discussed, an ontological and ontic structural realism have struggled to do justice to the original concept of those ideas, and have led to a lot of quite frustrated pieces of literature where people seem to be talking past each other. What I want to do in this lecture is kind of present or try to really state a version of structural realism that I think at least succeeds in realizing the broad kind of goals that the original proponents of epistemic and then ontic structural realism had in mind. There's a sense in which I'm not exactly going to defend this position, although obviously I kind of like it. My goal is not so much to say this is the right way to understand structural realism, or indeed this is the right structural realist way to understand the epistemology and metaphysics of science, but I want to at least try to put something down that's at least a clear enough target that, for instance, the opponents of structural realism in analytic metaphysics have something to get their teeth into. And the line I want to take to approach that is I want to start with what generally gets called the semantic notion of theories, or semantic conception of theories, although I'm not quite going to use that terminology. There's a sort of long-standing tradition that somehow there's some relation between structuralist ideas in the philosophy of science and the semantic way of conceiving theories. But again, quite how that gets cashed out gets messy and obscure in the literature, and one often gets the sense for a lot of the engagement with structural realism that it's kind of seen as a has an irrelevance, that this is some relatively technical question about what the precise formulation of theories is, but it doesn't make a difference to these kind of broader epistemological metaphysical disputes. I think that's not right. I want to cash out what I think the philosophically interesting and important distinction is between, again, what are traditionally called syntactic and semantic ways of conceptualizing theories. I want to cash that out in a way that's somewhat different how it's normally done, and I want to use that as a starting point to try to state and explicate the versions of structural realism I have in mind. I'll give a disclaimer that's particularly relevant for this kind of audience. I'm going to be, although I'm sometimes slipping into just saying science, I have really in mind physics here. So the kind of structuralist framework I'm going to discuss, the kind of way of presenting theories I'm going to discuss, is very much built around examples in physics, and I'm not really going to draw from outside physics. Part of that's just a matter of my own expertise, part of it's the context in which these discussions are had, and part of it is that physics is the easiest territory to defend a structuralist take on epistemology and metaphysics. If we can't make something like this work even in physics, then we probably can't make it work at all. If we can make it work in physics, then it becomes an interesting and open question to what extent these things generalize, and to what extent, if they don't, that tells us something interesting about the need for pluralism in the way we conceive the way the different subjects are set up. Okay, here's the distinction I want to draw between two ways of setting up theories. Suppose I want to present something like Newtonian mechanics. Well, the way Newton presented it, and the way one still thinks about theories as being presented in a lot of the sort of purer philosophy of science and metaphysics literature, is what theories are a collection of claims made in language about the world. This is where I can't scroll through this. Bear with me. Here we go. So here's a paragraph from Newton. Every body perseveres in its state of being at rest or of moving uniformly straight forward, except insofar as it's compelled to change its state by forces impressed. A change in motion is proportional to the motive forces impressed and takes place along the straight line in which that force is impressed. The common center of gravity of two or more bodies does not change its state, whether of motion or of rest, as a result of the actions of the bodies upon one another. So here we have a bunch of claims in interpreted language. I mean, originally in Latin, this is a translation, of course. My Latin is minimal. But in any case, what's fairly clearly going on is that we're talking about the world. We're talking about systems of the world. We're making claims in our language about the world, and we're glomming onto the world in the kind of way language gloms onto the world. So that kind of, call that a language first conception of what a scientific theory is. A scientific theory is a bunch of claims in language about the world. And that language first picture of a scientific theory is not a bad fit to the Principia Mathematica. It's not a perfect fit, but it's clearly going at a lot of what's going on in Principia. Principia really is making linguistic claims about the world. It's making claims about the world, if you like. A claim by its nature is a thing one does in language. Okay, but if you look at a 20th or 21st century presentation of Newtonian mechanics, it doesn't look anything like that. So this isn't actually from a particular textbook, I just made it up, but this is the kind of general form you'd get of a presentation of Newtonian mechanics in a modern mechanics text. A model of n particle Newtonian mechanics is specified by a list of n positive real numbers, m1 through mn, describing the particle masses. A list of n(n-1) smooth potential functions representing the two particle potential between the pairs of particles and being symmetric. A collection of n smooth functions satisfying such and such differential equations. Now, obviously, I've told you what that object is in language. There are language claims on the board here. I'm not telepathic. There are serious privacy issues if I were to try to inject a mathematical model directly into your brains, but even if you gave consent, then that's not something within my power. But the thing that's being presented in language is not a bunch of claims about the world. It's a description of a class of mathematical models. And that's that second conception of theories, call that a math first conception of theories. What we're doing in presenting a physical theory is presenting a class of mathematical models. The models in turn are supposed to stand in a relation to the world, but that relation is now not cashed out linguistically. Okay, this is very close to, arguably, a reformulation of the traditional distinction between a syntactic picture of a scientific theory and a semantic picture, with the syntactic picture being more along the first line and the semantic picture more on the second. But that way of thinking about scientific theories, almost since its inception, became very caught up in formalized notions. So that the attempts to make precise what a syntactic conception of a theory was ends up with a theory being some kind of collection of claims in some kind of formal language. And the development of the semantic perspective on theories very quickly gets caught up in set theoretic conceptions of models and set theoretic modelings of physical theories. So famously, at least as quoted by Van Fraassen, I've actually struggled to track down the original, famously Sitter said that we want mathematics, not metamathematics, for the foundations of science. But what we actually end up doing very quickly was a different kind of metamathematics, set theory rather than logic. I think that kind of formal route is misleading as a way of thinking about what's at stake in the discussion. I think that's understood in various other bits of the literature, but not in some of the core physics-motivated bits of the philosophy of science literature. I think it elides away a lot of the difference, because once one has in mind that a theory on the syntactic conception is some formalized set of claims in language, and a theory on the semantic conception is a set of models in the set theoretic sense of model, at that point one finds oneself gesturing in the direction of the completeness theorem and the idea that there's some trivial isomorphism back between these frameworks. So one of the reasons I want to use this sort of somewhat novel terminology, language first, math first, is rather than the standard terminologies, I think that's even that use of the word semantic, and more generally the ideas built up around that, suggests a formalized notion here that doesn't get to the core of the interesting distinction. Again, I don't claim that as a novel observation, but it's underappreciated, I think, in the sort of core scientific realism, structural realism literature. And the other reason I want to talk about language first versus math first, apart from the fact that I want to focus on those informal features, is I want to be a bit blurry and vague about this. There's clearly bits of mathematics in the Principia. It's entirely plausible and compatible with my framework that it might be that the right way to think about scientific theories is math first, and yet there's irreducible aspects of language work, and maybe vice versa. But I want to say that there are kind of rather clear and important differences that come from this way of thinking about theories that we can hold on to even if the exact boundaries get blurry, and that do a lot of work in thinking about how the sort of standard debates on scientific realism and structural realism play out. So rather than give a sharp statement of these distinct frameworks, I want to give and I want to illustrate the ideas by three sorts of examples of why the difference between a math first and a language first conception of theories matters. By the way, I should say, the last time I used these slides was in the UK, and I very carefully changed back to talk about maths. I don't think I've entirely changed back to represent my American roots for this talk. And I should say, it's perhaps worth saying, what are we actually saying when we say, okay, the right conception of theories in physics is along the math first or language first line? I don't intend that to be something like merely sociologically descriptively. If you sent the sociologists into the physics department and asked them to reconstruct what is this thing called a theory, that they'd return the language first or math first framework. I think it's pretty clear the thing they would return would be a somewhat complicated and messy kind of entity, perhaps closer to something like a Kuhnian disciplinary matrix or something with all sorts of different aspects mixed into it. I have in mind something like, what does the rational reconstruction of a theory look like? And I don't want to push too hard on that line, but there's in some sense that's vague, in which I hope to sort of explicate through examples rather than state sharply. There's a degree of normativity about what I mean when I say we should think about theories in such a way. And in case it's not obvious, my sense is that the math first conception of theories is a much better fit to how you would describe the knowledge we've got out of at least the physics of the 20th and 21st century. But I'm only going to argue that indirectly by showing how these differences come up. And precisely because I think there's a certain degree of normativity to this, there's room for sharp critics of modern physics, like, say, Tim Maudlin, to say, well, sure, sociologically, it's true that the way physics is done is along these math first kind of lines, but this is just one of the various ways in which physics has lost its way. Okay, all that as a matter of preamble. Let me talk about why the distinction matters. And I want to identify three ways it matters. One is the way in which theories make empirical predictions. One is the notion of formal equivalence of theories we get. And one is the account we get of intertheoretic reduction. So to start with empirical predictions. Here's the difference, I think. On the language first account of theories, the way theories make contact with data is they say true things about the data. So on a language first conception of Kepler's laws, for instance, the way Keplerian mechanics makes contact with the world is Kepler's theory says planets move in ellipses with the sun at one focus, and planets do indeed move in ellipses with the sun at one focus. On the maths first sense, theories make contact with data by accurately modeling them. On that perspective, we have in the traditional sense something like a data model of the positions of, say, one of the planets orbiting the sun. That model is cashed out mathematically. It describes some curve through Euclidean space. The theory says that the models of this are given by certain curves through Euclidean space, and the curves are close matches, or ideally exact matches, to the data given. So this is a distinction between saying true things about the data versus providing a mathematical model of the data. Okay, why does that matter? Well, here are two reasons it matters. First observation, it's not true that planets move in ellipses with the sun at one focus. The best we can do is say something like it's approximately true that planets move in ellipses with the sun at one focus. But it's very tricky to pin down what this notion of approximate truth actually means. Formal attempts to give a syntax and semantics for approximate truth have largely floundered. If you look at sort of approximate truth discussions in real life contexts, mostly approximate truth ends up being a bit of a euphemism for false. So if my wife says, "Have you been faithful to me?" and I say, "It's approximately true I've been faithful to you," this is not a reassuring response. The sense in which we seem to be doing something slightly more than just saying false in a nice way in a physics context seems to be that the statement planets, it's approximately true that planets move in ellipses with the sun at one focus is elliptical, so to speak, for something like it is true that planets approximately move in an ellipse with the sun at one focus, which in turn, by disquotation, is just another way of saying planets approximately move in circles of the sun at one focus. The notion of approximate truth, the idea of some broader semantic notion, has just fallen away entirely. Now, on the math first conception of a theory, it's a lot cleaner. The idea here is going to be what the theory is aiming to do is to model the data. And what we're actually doing is we're approximately modeling the data. The planets don't move in ellipses, they move in approximate ellipses, and one can cash out the degree of approximation by saying, for instance, what's the root mean square difference between the actual trajectory and the best fit ellipse I can put averaged over the orbit. I've got access to domain-specific modeling tools to measure closeness of fit. I can get at those kind of indirectly in a language first framework, but only really by looking to the mathematics. The math first framework gives us resources to rather more directly get at the idea that my theory is only approximately right. Okay, here's the second way in which I think it matters. It's often not true even that planets move approximately in ellipses with the sun at one focus. Yeah, forget which comet it was. Should make Olivia? It was like I forget its name. There was a particular comet about 20 or 30 years ago, which was doing a great job in moving an ellipse with the sun at one focus until it hit Jupiter, at which point it ceased to be even faintly true. Even that's a little quick. A little bit before it hit Jupiter, it was being seriously messed around by Jupiter, and the elliptical description stopped being even faintly correct. So what do we mean by we say it's approximately true that planets move in ellipses with the sun at one focus, or bodies, I suppose, comets aren't planets? Maybe we're saying something like, well, most planetary bodies move in ellipses with the sun at with the sun or their star at one focus. Is that true? I don't know if that's true. There's a lot of binary systems out there. I don't think it's completely clear how many binary systems have planets. If binary systems have planets, they move in weird, complicated, squiggly patterns. So if we're just doing a count, then the statement that most celestial bodies move in ellipses with the sun at one focus looks to me shaky. It might be true, it might not. But in any case, who cares? That doesn't seem salient or relevant to the applicative usefulness of Kepler's laws. What matters there is never mind how many other bodies may or may not move in ellipses of the sun at one focus. These ones do, approximately. Restricted to the domain of the solar system, or restricted more generally to those domains which can be adequately treated as two-body problems with one body much larger than the other, things approximately move in ellipses. And when things don't get too close to each other in that framework, so you don't get close disruption, then things move in ellipses with the sun at one focus. In other words, what we're really after with our scientific theories is not well cashed out in the notion we want the theory to be true. The best we want is something like the theory should be true of these kind of systems with respect to these kind of descriptions. That kind, you can make that work with a certain amount of effort on a language first version, but you need to rethink the semantics of those language claims in a way that's quite non-transparent and not often picked up in the more a prioristic discussions of scientific realism. The math first conception, it's kind of more immediate and transparent. It's kind of reasonably obvious that more or less any physics model, when it says we're trying to model the phenomena, is not trying to model the entire universe. So the very idea of using something like an n-body Newtonian model to model the motion of the planets is always going to be something like we're trying to model, this is going to model certain systems. It's going to do it multiply, it'll do it to different degrees of accuracy in different places. If you go back to my version of Newtonian mechanics here, if I give you that theory and you say, yes, but what's n? Tell me the value of n, you're missing the point. This is a modeling template to which multiple things fit. So that kind of domain restriction idea is, if not inaccessible on the language first framework, at least much more directly accessible and natural on the math first framework. Okay, that was my first set of reasons. Here's my second set of reasons. Think about formal equivalence between theories. So I should say as a disclaimer firstly here, it's of course true that our notion of equivalence between theories is never going to be completely cashed out just in a formal way. So you know, the Langevin equation for stochastic processes models classical Brownian motion pretty well. It models more abstract features of classical mechanics, like the variations of the energy of some non-closed system. It models stock market prices quite well in a certain framework. We obviously don't want to say that I can just look formally at the math of the Langevin equation and say that I can understand its content and just from that formal structure. Nonetheless, at least in physics, it's explicitly clear that we do operate with some formal notion of theoretical equivalence, particularly when we're talking about new theories developed to describe new domains with some common starting point, where we are using something like, when can I relate two theories formally? And the notion of formal equivalence plays out very, very differently on the language first and math first framework. So on the language first approach, formal equivalence is something like synonymy or intertranslatability. The theories are saying the same things, making the same claims. So Principia in Latin, in the original Latin, is not a distinct theory from the English translation of Principia I was drawing my example from earlier. When physicists were thinking that maybe the proton has substructure, Feynman called the substructure particles partons, Gell-Mann called them quarks. Insofar as they were different, as Feynman and Gell-Mann were developing different theories, it wasn't just because they chose different words. What Feynman meant by parton and what Gell-Mann meant by quark were the same. And insofar as we formalize our theories, of course, that formal notion of intertranslatability comes across to various kinds of first order logic or higher order logic conceptions. On a math first conception, then formal equivalence is more something like mathematical equivalence. That's a vague and pluralized notion. Sharpening it tends to run into counterexamples, but routinely across mathematics and the mathematical corners of physics, we use some idea that different mathematical structures are mathematically equivalent, have some kind of generalized notion of isomorphism between them. And on the maths first conception of theories, that's what we have in mind when we say two theories are formally equivalent to each other. All right, why does that matter? Well, the notion of math first equivalence you get, the notion of equivalence on mathematical grounds, is much, much coarser grained than a language first notion. Many, many things that don't come out as equivalent if we have a language first conception of formal equivalent come out equivalent on a more math first notion. So to illustrate, Euclidean space is a nice example. So if I want to formalize Euclidean space, I can do it Klein style. I can say Euclidean space is a set plus an infinity of bijections from that set into R3, R cross R cross R, such that those bijections are related, any two of those bijections are related by a Euclidean transformation of R3. In other words, a transformation of R3 that preserves linear structure and distance structure on that space. That's one mathematical way I can formalize Euclidean space in terms of an infinitude of coordinate systems. I could also formalize Euclidean space as an affine space with an associated Euclidean vector space. I can formalize a vector space in an algebraic way. I can formulate an affine space as a set with an appropriate action of the vector space on that affine space. I can also formulate Euclidean space in the language of differential geometry. I can say I've got a manifold, you know, a set within infinite equivalence classes of maps into R3 related by smooth transformations, and with a certain tensor field written on that manifold, where the tensor field succeeds in defining a metric, and with an appropriate flatness condition for that metric, so it turns out flat. Those mathematical structures, by the standards of mathematics, are equivalent. I can move between them easily and happily. If you try formalizing them in language, then their assumptions about what things exist and how many things there are start breaking down quite badly. It's very hard, unless you sort of basically reverse engineering it from the mathematics, to write a translation scheme between an in-language description of the theory and of one of those mathematical descriptions and another such. Classical field theory is another example, which was significant in the development of structural realism. If I think about a field, mathematically, I represent the field, let's say a scalar field for those who come to my QFT class. Mathematically, the scalar field is a map from space or space-time, however we formulate that notion, to the real numbers, assigns a real number to each point in space. I could think about that as saying, well, the objects in my theory are the points of space, and I'm assigning a certain quantity to every object represented by a real number. Or I could say, well, the object is the field and the parts of the field, and the parts of the field have both field strengths and locations in space and time. Mathematically, you can move directly back and forth between these. Mathematically, these are equivalent. But if you look at what the quantifiers range over, what we're saying exists on these frameworks, it's going to come out different. On the first framework, the only objects in the theory, the only things over which we quantify, are the space-time points. In the second case, we have a dualistic ontology, consisting both of space-time points and parts of an extended object, the field. And in this case, I actually have direct evidence that the former notion of mathematical equivalence, the coarser one, is the one that physics use. About 10 years ago, I wrote a paper basically developing the second, a natural way to think about the second way of doing a field theory in the context of general relativity. And I submitted the paper to Physical Review D. Physical Review D desk rejected it on the grounds that they don't publish reformulations of existing theories. So at least in that case, I've checked with the physics community and they say yes. Okay, the third example is drastically more complicated. I'm going to need to pause for about a semester to talk, maybe not on reflection. The ADS-CFT correspondence is a complicated duality between two theories in modern quantum gravity. The ADS theory is, roughly speaking, general relativity and string theory on a space-time which asymptotically looks like empty space with a negative cosmological constant. The CFT is a field theory of a certain kind, a quantum field theory of a certain kind, on the boundary of that same space. So these two theories, and it's really important to recognize these are supposed to be equivalent to one another. So when I say it's on the boundary, I don't mean the stuff in the middle is there as well. I mean, I've got description 1, which does my physics on a curved n+1 dimensional space-time, and I've got description 2, which does my physics on a flat n-dimensional space-time. Description 1, my physics is a physics of strings and curvatures and things. On theory 2, my physics is a physics of field strengths. So these are frameworks that don't even agree on the dimension of space-time, let alone on what objects there are. Any plausible attempt to cash them out in linguistic terms is going to struggle to represent that as a genuine equivalence and intertranslatability. And yet it's just routine in quantum gravity that these are just the same theory differently presented, or at least insofar as it's not routine, the lack of routineness is about technical challenges to whether one indeed can construct the appropriate isomorphisms, not the view that there's a further question to ask once they're constructed. Okay, there's a general theme now I want to pull out. What math first equivalence does is mix up ontological categories. It gives me transformations between mathematically equivalent descriptions that look very different when you start saying, what are the objects according to these things? What are the properties they have? So I introduce a bit of terminology I want later. Given a mathematically stated theory, a predicate specification of that theory is a description of the theory in object property relation terms. And then the point's going to be that a single mathematically stated theory can have many different predicate specifications that can't be translated straightforwardly one to the other. And that's the slightly more precise sense in which the maths first conception has a coarser grained notion of intertheoretic, or sort of theoretical equivalence than the language first version. Okay, here's my third reason why it matters. Think about intertheoretic reduction. So here's the difference. On a language first conception of theories, intertheoretic reduction is something like logical derivability or deducibility. This covers a multitude of sins, but that's the sort of core idea that we can track back to the logical empiricists. I reduce theory 1 to theory 2 because somehow the claims of theory 2 are the axioms of theory 2 are theorems of theory 1. And to do that, of course, therefore requires something like I need bridge laws because some of the vocabulary of theory 2 might not even be in theory 1. If theory 2 is thermodynamics, for instance, and speaks of heat and temperature and volume, and those simply just aren't terms present in statistical mechanics, I need bridge laws to introduce those just as a matter of logic. And then with the bridge laws, I can derive the theory. On the maths first view, reduction is more something like structural instantiation. I've got one mathematical theory, and I want to show that that mathematical theory can be realized in the structures of a lower level mathematical theory. So for instance, if I'm doing solid matter, then my description of the table as a solid matter description with vibrational waves through it is something like a continuum description. If I'm describing the table, ignore quantum mechanics for now, in terms of its particles, I'm going to have a description of particle locations. I can do something like take the Fourier modes of the particle locations. I can restrict attention to the lower frequency modes, which will give me a description varying only over long scales. And then I can say that the low frequency mode part of the Fourier transform of the atomic description has the same mathematical structure as the continuum description. That's the kind of move you might make in a maths first notion of structural reduction. Why does it matter? Well, among other things, the language first reduction has a problem that I sort of gestured at when I was talking about bridge principles, a problem of new ontology. So very often the higher level theory is talking about things the lower level theory wasn't talking about. My table has continuous matter with densities and things like this. My atomic theory didn't have those things in it. The kind of go-to metaphysical move people have in mind to address this is something like mereology. And you see this in some of the early reduction literatures. You see Oppenheim and Putnam appealing to that kind of thing in their classic discussions of reduction. The idea is somehow I introduce mereology, so my particle theory doesn't just include particles, it includes mereological sums of particles. Even that doesn't do super well, even for the case of the vibrational modes of the table. I mean, even the mereological sum of all the atoms in the table doesn't occupy anything like all the space that the table occupies, a familiar concern about these moves. And the form of reduction we actually used went via a kind of Fourier analysis. I mean, when I do that Fourier analysis thing, I'm giving you a quick verbal description of what we actually do in deriving solid state dynamics. It doesn't match in a super good way the kind of thing we get out of mereology. It looks more something like a modal analysis of some collective features. But the table is a relatively friendly example. I mean, I use tables about gases for no good reason. The gas has just the same kind of features. Gases fill the box. The mereological sum of particles does not fill the box. Take protons. The proton is composed of 3 quarks, the popular science books will tell you. And one naturally thinks about a proton as being the mereological sum of 3 quarks. The proton is not the mereological sum of 3 quarks. The view that the proton is composed of 3 quarks, depending how generous you're feeling, is somewhere between, apologies to my QFT class, I think I used the same comment a couple of days ago. The view that the proton is composed of 3 quarks is somewhere between a heuristically helpful verbal gloss and a tale that we tell to children. The real story is something vastly more complicated, much more structural, much more dynamical. It's about taking the field theory of quarks, analyzing at low energies, and finding that certain collective degrees of freedom of that theory at low energies have a pole in the multi-point functions that describe them that can be interpreted as a localized excitation of the mass of the proton. Going back up to classical mechanics again, if you think about waves, it's perfectly natural to talk about a wave on the sea or a hurricane or something. We talk about this as persistent objects. We can perfectly well say that earthquake created a tsunami. The tsunami wave moved out and it was initially here and in due course was here, but now has gone. But of course, at the level of water molecules, you can't identify the tsunami wave simply with the water molecules, even more so with ordinary non-tsunami type waves, where the wave can be moving along while the water molecules themselves are just going up and up. So what we have is a situation where the objects at one level are supervening not on objects at a lower level, but properties or relations or something at a lower level. So we have a sort of an ontological discontinuity that's happening in intertheoretic reduction. So imagine I've got theories low and high. So low is the low level theory and high is the high level theory. That sounds trivial, but if it was low energy and high energy, we'd reverse the whole thing. So the high level thing is the thing that I want to reduce to the low level thing. So supposing these are mathematically presented theories, and suppose I've got a mathematical reduction of the high level theory to the low level theory. And suppose that PP low and PP high are the predicate precisifications, respectively, of the low level theory and the high level theory. Well, none of that gives you any particular reason to expect a simple relation between the ontologies of the low level predicate precisification and the high level predicate precisification. Okay, so those are my distinctions between math first and language first approaches. Now I want to turn around to the scientific realism debate. So suppose that the language first perspective of theories is right. And I think this is tacitly presupposed by an awful lot of the traditional scientific realism debates. On the language first perspective of theories, what does scientific realism look like? Well, it makes the following kind of claims. Firstly, scientific theories are true, or approximately true, even about unobservables rather. So if the relation between theory and evidence on the language first view is that theories try to say true things that, about the empirical data, well, for scientific realists, they try to say true things and significantly succeed in saying true things, even about stuff we can't see. So we take the idea that the theory world relation is truth and reference, and we move it from the empirical subdomain to a larger chunk of the domain, maybe the whole domain. Secondly, we've got a significant, potentially serious problem of underdetermination. We have, even in situations where we've collected all the evidence, we have a concern that, at least potential concern, that there can be multiple distinct but empirically equivalent theories. And a standard go-to move in the scientific realism literature would be to appeal to extra empirical virtues like, simplicity, elegance, explanatory power, to try to resolve these questions of underdetermination. Theory change is a potentially serious problem because we seem to have historical examples where, although the empirical content of theories is largely preserved over theory change, the non-empirical, unobservable claims about the theory get convulsed. We don't think there's an electromagnetic ether anymore. We don't think caloric is a fluid anymore. And there's a bunch of moves you can make responding to this, but I think you can dump a lot of the moves in traditional philosophy of science literature here under the label of selective skepticism. So, for instance, the scientific realist is not supposed to believe all the claims of the theory, but only those claims which do explanatory work in the subsequent theory. There's some sense in which we're looking for a principle and not just ad hoc and anachronistic reason to look at a theory and say, don't believe all the things it says, but here are the things that you can be confident in believing, because here are the things that are pulling their weight explanatorily, and so here are the things that will continue into the next theory. And the classic criticism of that coming from skeptics will be that all of this is kind of ad hoc and made up retroactively. There's also a kind of continuity of analytic metaphysics with science here, because science is trying to say true things about the world. So on the modern, less kind of Swilsonian conception is metaphysics. And metaphysics is saying more and finer grained things about the world than science, but it's at least starting with the things that science says. Here you have something like Quine's conception. It still has a long shadow over modern metaphysics. Science is telling you some of the truths, but there might be more truths that the analytic metaphysician can fill in that scientific evidence won't speak to. And how can that be done? Well, the standard defense you'll have of the methodology used by metaphysicians in this tradition is that the way they decide between their distinct theories of, say, tropes versus processes, or different grades of mereology, or is that they're using the same kind of explanationist methods that scientists use to resolve underdetermination, and the methods are continuous to the scientists, and they can to some extent inherit the virtues of the scientist and justify them by appealing to the justification of the scientist. So that's a kind of very rough, slightly unfair gloss of what scientific realism looks like on the language first conception. What does structural realism look like if we hold on to the language first conception? And I want to say that I think, at least inside the the physics adjacent literature, a huge fraction of the attempts to develop structural realism have happened explicitly or tacitly within that language first conception of scientific theories. Well, epistemic structural realism, the idea that somehow all we can know about the world is its structure, even though there are non-structural features of the world, that starts becoming a form of selective skepticism. It fits into my general framework that selective skepticism is the general format of how the realist responds to the worry of theory change. So the idea is that if the Van Fraassen style constructive empiricist only believes the observational claims, and the naive realist believes all the claims, then the epistemic structural realist believes the structural claims, which exceed the observational claims, but fall short of all the claims. And then the idea is going to be somehow, hopefully, that commitment to believe the structural claims is going to be more principled and more resistant to kind of criticisms of ad hoc anachronism than other such forms of selective skepticism. And ontic structural realism becomes something like a priority thesis. Here we get this kind of talk of relations rather than relations without relata, or relations first, object second. It's something like, whereas a traditional metaphysics would say you start with objects and then relations are things that hold between objects. So somehow the structural realist says that relations are logically prior to objects or metaphysically prior to objects. Maybe we can dispense of objects entirely and just say they're places in the network of relations. But in any case, there's some sense in which relations have more of the metaphysical status. And language first structural realism runs into a lot of trouble. And this is the kind of tangle I was talking about at the beginning of the seminar. So the huge problem for language first epistemic structural realism is it's really hard to consistently distinguish a notion of structural content that's genuinely intermediate between observational and all content. So one extreme, you find people like Silos, who's a sort of classic realist, saying, well, look, all I really believed in is structure. I never thought objects had these kind of unobservable Wassilian natures that transcend everything structural. So my position was already a structural realism, and any sensible scientific realist is already a structural realist. At the other extreme, you get people trying to do sort of Newman-type moves where we precisify structural realism by saying we'll just quantify overall the unobservable relations. So we'll say not my theory has relation R that holds between such and such objects, but just there exists X such that X is a relation and holds between these objects. And we've seen the kind of criticism, the sort of logical criticisms of the Newman objection that basically says that collapses straight back to observational content. So in other words, on the one hand, Silos is saying your attempt to develop structural realism collapses all the way into straightforward realism. The other extent, the Newman objection says that attempt to develop structural realism collapses right back to observational. So, some kind of instrumentalism. There's a failure to identify and hold on to a position that's genuinely intermediate. And the problem for the language first approach to ontic structural realism, it gets really metaphysical really quickly. And there's a kind of rather delicious irony in the fact that the most strident advocates of ontic structural realism, like James Ladyman and Steve French, particularly Ladyman, are ferocious critics of analytic metaphysics, and are kind of famous for this among the analytic metaphysicians. But if you look at the way the actual literature on ontic structural realism trying to develop these priority theses go, it goes really deep into metaphysics, well clear of anything you're getting in a naturalized way. And I think a problem for both of these is that if you go back to the original motivations for structural realism from underdetermination and theory change, they're not really being addressed in this kind of framework. Trying to build a Ramsey sentence version of electrodynamics doesn't look very likely to capture the apparent continuity at the level of equations we see between ether theory electrodynamics and Maxwellian electrodynamics and quantum electrodynamics. Okay, so obvious proposal I want to explore. How about if we take the math first conception of what a theory is and then ask what does scientific realism look like on that basis? Well, if we you can't literally say I have a math first perspective on scientific realism and I will be a scientific realist in the standard sense, because a scientific realist in the standard sense is committed to the fact that our best theories, at least in some idealization, are true. And truth is a kind of thing you can attribute to sentences or propositions or other claims in a language. Truth is just not syntactically something you can attribute to a mathematical model. Mathematical models aren't in the business of being true or false. They're in the business of correctly or incorrectly modeling, or actually or inaccurately modeling. But it's pretty obvious how you rephrase scientific realism to reflect that. What we want to say is, just as the empirical success of a scientific theory says that it successfully models the empirically accessible data. So the full-on math-first scientific realist says that a scientific theory successfully models all the data, including the unobservable data, maybe only to some degree of approximation. Now, from that point of view, underdetermination becomes a lot less serious. I mean, the positive cases for realism look fairly similar in both cases, but the negative cases look different. So if you look at most of the genuinely problematic cases of underdetermination, they tend to involve cases where I've got mathematically equivalent theories that somehow we think are nonetheless empirically distinct, nonetheless content-wise distinct. So the classic example is curved space-time pictures of gravity versus gravity as a force. In fact, you can make a reasonable case that, given the theory ladenness of observation, we can never really have a conclusive argument that two theories were empirically indistinguishable unless we showed that they were mathematically equivalent. And a variant of that is John Norton's observation that, at the very least, an argument to the effect that two theories are empirically equivalent that doesn't train them being mathematically equivalent is not going to be short enough to fit into a philosophy paper. And theory change, likewise, as something thought about internal to science, never mind the metaphysics of this, again looks much less serious. Theory change between mature theoretical physics nearly always leaves the old theory instantiated by the new theory in inappropriate regimes. So a large amount of the kind of criticisms of scientific realism coming from underdetermination theory change actually aren't really even stateable if what you had in mind by a scientific theory in the first place, or again, a physics theory in the first place, is cashed out primarily in the sense of a class of mathematical models. And I want to suggest that actually, and I think, again, in some ways this is tacit but not pulled out in some of the structural realist literature, there's a sense in which the mere move to a math-first conception of the theory is already structural realism, at least the epistemic sense. The content of what Worrell and others had in mind by saying we want structural continuity was really mathematical continuity. And once our conception of what a scientific theory is mathematical or maths first, we actually get already most of that set of ideas. Okay, but the traditional scientific realist might be worried that we want to sort of throw the baby out with the bathwater, because maybe one only gets that by having to row back a lot on our conception of what we learn about the world from a scientific theory. So let's ask, what does standard metaphysics look like if we hold on to this maths first conception of scientific realism? Well, on the standard understanding of metaphysics, even a completed scientific theory underdetermines its metaphysics. Because our metaphysics is kind of the objects, the properties, the relations they have. Our scientific theories are much more coarse-grained than that. That's the sense in which you can think of this as a form of epistemic structural realism. The structure is given not by some subset of the claims in language in the theory, but by the mathematical structure, and the linguistic descriptions are underdetermined by the mathematical structure. So roughly speaking, I think you can say, using my earlier notion of predicate for sissification, what a metaphysics is for a scientific theory is a predicate for sissification of that theory. And then, of course, the underdetermination is coming in the fact that there are many predicate for sissifications for the same piece of mathematics. And then the normal methods of metaphysics would be used to decide between predicate specifications on the grounds of simplicity, elegance, clarity, intuitive naturalness, whatever other things count as the metaphysical good stuff. Although on that conception, the motivation of these is much more tenuous because we no longer have the continuity between scientific realism and analytic metaphysics that's being relied on by one of the standard defenses of the metaphysical method. Ex hypothesi, the kind of underdetermination the metaphysician is dealing with is not the kind of underdetermination that the scientist is dealing with. And so if we're resolving, for instance, whether we should have a curved space-time or force version of gravity, we can't appeal to science to get the tools to do that, because science on the structuralist reading here doesn't care about whether we understand general relativity in terms of forces or curvatures, except at most as a kind of pedagogical convenience, but not as anything effective. So I think that's a plausible way of cashing out how to think about epistemic structural realism. But I think there's also a natural way of thinking about ontic structural realism. Remember, the ontic structural realist had in mind that we shouldn't even have a metaphysics that went beyond the structures given us to science. And I think there's a natural way to do this in this framework. We can say, well, metaphysical theories, just like physics theories, ought to be representations of the system, perhaps the universe, by a mathematical structure rather than describing it in predicate logic. So, I mean, there's a very common metaphor used by metaphysicians that what they want to do is to learn about the book of the world. So on a maths first conception of what metaphysics is, there is no book of the world in the sense of the most fundamental description of the world given in some idealized language. What there is the maximally descriptive mathematical model of the world. And insofar as that's viable, that's a form of ontic structural realism. There's no underdetermination in metaphysics by physics. Okay, so that's kind of the end of the core framework I want to give. But for the last few minutes, I just want to talk a bit about how we make our way back from that kind of structural take, which again, to clarify again, I haven't really defended, just tried to state cleanly. How we make our way back from that kind of framework to something that's more in the business of talking about what the objects are in the world and the properties they have in a way that metaphysics wants us to do, and which we ourselves find ourselves wanting to do all the time in our ordinary discourse and our pedagogy. And I think the clearest way to think about objects on a structuralist conception of physics is following this kind of idea from Simon Saunders. So Saunders says, the notion of object is clearest in logic in the structure of the proposition, but the language of physics is mathematics, not the predicate calculus. I mean, I think you should think of him using language metaphorically. I'd prefer to say the representative machinery of physics is not language, but I think that can just be terminological. Not all, and perhaps not even the most important parts of what physicists know can actually accurately be put into words. We must do our best to say what there is, so there'll always be a place for objects understood as objects of predication, but I see no reason why objects in this sense should precisely line up with the constituents of reality, whatever they are, given that the primary vehicle for understanding reality is mathematics. In other words, we do want to seek descriptions of the world in language in terms of what the objects and things are, but the descriptions may well be imperfect. They may not capture everything. They're partial, and in that sense, they're secondary. So here's my precisification of Saunders' idea here. Claim is going to be that on a structural realism of this sort, actually both on the epistemic and ontic version, what we mean by the ontology of a mathematically presented theory is it's the best predicate for sissification of that theory, the most perspicuous, the simplest, the most explanatory. But on the math first conception of epistemic structural realism, it's the ontology that's the more fundamental. In the metaphysician's term, it's the ontology that grounds the mathematical description. And so our reasoning, going from the thing we get from our science, the mathematized description, to our description in language, the predicate for sissification, that method is something like IBE reasoning. It's something like, because this predicate for sissification is the best fit to the mathematical theory which X hypotheses have evidence for, that's evidence that that predicate for sissification is the true underlying metaphysics. The methodology of that, I think, looks the same on a math-based version of ontic structural realism, but the interpretation is really different. From that point of view, the mathematical presentation is the fundamental thing, the ontology is the secondary thing. And therefore, our specification of the ontology can be a bit pragmatic, if you like. It might actually be that the reason we want one predicate for sissification rather than another turns on relatively contingent things about what we find explanatory or pedagogically helpful or convenient or simple. And we might even prefer different assignments of ontology to a mathematically presented theory for different purposes. And that gives us an interesting story to tell about the ontology of higher and lower level things. So suppose I've got my low level theory and my high level theory, and they're both mathematically presented. And therefore my low level theory instantiates the high level theory and metaphysically speaking, grounds the high level theory. For the ontic structural realist, who thinks that the mathematical description is primary, then the low-level theory grounds the low-level ontology. The low-level ontology is the most perspicuous, most helpful predicate for sissification of the low-level theory. Likewise, the high-level ontology is the most perspicuous presentation in language of the high-level theory. There need be no simple relation between them. We saw that when we discussed interthetic relations earlier. There can be wild ontological discontinuity. Dennett talks about real patterns as the way he understands higher-level ontology and low-level ontology. And on this kind of conception, I think what it is for an object in the higher-level ontology to be an object in the low-level ontology is simply to be a real pattern. The low-level ontology is simply for it to be the case that the object in the higher-level ontology is what is part of the best ontology we can assign to the high-level theory, and the object in the low-level theory ontology is in the best ontology I can ascribe to the low-level theory. And It might be that sometimes I can find relations of mereology or other forms of composition between them, but if I can't, so be it. If we had the epistemic conception, where ultimately there's a true low-lying metaphysics that grounds the low-level mathematical description, then it becomes much more puzzling how to think about the relation between the low-level and high-level ontology. And you can kind of work through the possibilities. So however we set it out, on that framework, the low-level ontology grounds the low-level theory. In other words, the low-level theory of mathematics is true because it's the mathematical structure given by the precise ontology. And the high-level theory, in turn, is instantiated in and therefore grounded by the low-level theory. But what about the high-level ontology? Well, here's some options. We could say, look, the high-level ontology is grounded in the low-level ontology. The reason the high-level ontology is true is something is what it is because of what the low-level ontology is. Incidentally, this is something like what Bishin calls the ontology first picture of interthreaded reduction, I think, where we have the idea that somehow I can directly understand a relation between the high-level ontology and the low-level ontology. But on that framework, it's very hard to understand how I think about the relation between the high-level ontology and the high-level theory. They seem to have come apart. And our ability to do things like, refer to, say, the viscosity of thick fluids in a reduction of fluid mechanics to a low-level theory starts being unclear. Viscosity seems to be one of these things we get at through the physics dynamics, but we've sort of lost our track of what the relation is between the high-level theory and the high-level ontology. Or we could try saying, well, look, maybe the high-level theory ontology grounds the high-level theory, just like the low-level ontology grounds the low-level theory. But now we've lost track of quite how the high-level and low-level ontology are connected, and what any of that's got to do with the fact that it's also supposed to be the case that the high-level theory mathematically is correct, is what it is because it instantiates the structure, because its instantiation the structures the low-level theory. Or we could say, and this is the only thing I actually think is really consistent for the epistemic structural realist, that although the low-level ontology grounds the low-level theory, the high-level theory grounds the high-level ontology. In other words, low-level ontology is special, fundamental ontology is special, which is a line congenial to many philosophers of physics and analytic metaphysicians. Somehow the lowest level description really is the only level at which we can really do ontology. So really the way ontology works is it's fundamental ontology. It's the ontology that underpins our most fundamental physics. And then all that stuff about higher level stuff is practical instrumental stuff that we don't care about. Well, I think that's consistent. There is a small problem. We don't have the low-level theory yet. If the game of ontology is to work out the right ontology for our fundamental physical theory, then the right thing for analytic metaphysicians to do at the moment is to work on developing our lowest level our fundamental physical theory. Or more realistically, given relative skill sets, the most useful thing for analytic metaphysicians to do is probably to retrain and do ethics or something until and unless a lower level theory is developed. So on that conception, if that conception were correct, I think actually it makes the project of doing metaphysics hard to motivate, because what that now says is that the story of doing ontology at higher levels is fundamentally different from the story of doing ontology at lower levels, at the lowest level. And we don't have the physical theory of the lowest level. Okay, let me wrap up. A mathematics' first conception of physical theories leads naturally to a form of ontic structural realism that seems to realize the main goals of the ontic structural realist program. And I should say also a form of epistemic structural realism likewise, but I'm more focused on the ontic side. And a notion of ontology that's robust but secondary, and which ironically in being secondary actually provides a rather better justification for the methods one uses in metaphysics, precisely because we're not looking for something deeper. We're looking for something that's emergent from, helpful because of our lower level, more mathematized description. And an ontology that's fundamentally disunified, where there's no kind of uniform way of saying what there is at all scales and all times, no mereological or other kind of relations between objects at one level and another level, but which doesn't require from that disunified ontology a disunified metaphysics. From this sort of story, the question of whether we can have a unified metaphysics is a question about whether we can have a unified structure of science. And that question isn't a philosophical question. It's going to turn on your assessment of how successful or otherwise we've been in actually understanding the instantiation relations as a whole between various bits of the world, of our physical and ultimately scientific theories at different scales. So Nancy Cartwright has a fundamentally disunified picture of the world because she thinks she's very pessimistic about how well we've actually done outside stylized contexts in seeing how theories at different levels relate to each other, and she thinks claims about those relations are overblown. I'm more optimistic about that than Cartwright, at least in the domain of physics. I think we have a rather rich and developed notion of intertheoretic relations of this kind, and it's compatible with thinking that the higher level theories in physics are what they are because of what the lower level theories are like. But that's a scientific disagreement. And its starting point is a point where we have, we're kind of committed to a disunified ontology because of the disunified nature of science, and the sense in which it might or might not be unified at the structural level is an open scientific question. Okay, let me stop there. Thank you.
A little break and then we'll come back for questions. And when you want to raise your hand, tell me your name so I can write it down, and then we'll do that. I thought they were computers to try to squeeze them, but this one wasn't.
Okay.
Is that starting from today, Mike? 2:30. Okay.
I sent out a notice.
Oh, but after I started looking at them.
I have a mini group that goes till 3:10, but I might pop in. Yeah.
All right, well, let me hang around. Get some for me. Okay, that was my parts of it. I certainly have questions.
Great.
They may be naive, but those-
Well, those are usually the most dangerous questions.
I'm the only because I can't think and write. I knew that. I knew that, but I didn't know that. You're first. I'm gonna put myself back. We'll have a serious question, then we'll have mine. What?
That's it? Oh, I've had I think a Pinex is kind of it.
I'm not gonna let myself go first. That's the benefit of making.
Sure, yes. That's always the curse of having to chair.
I know, but I did put myself.
Like you actually, if you're chair, you absolutely have to have a question because you need to ask if awkward silences, and yet you may never have a chance to ask a question.
That's right. So that's, I treat myself, I distance myself from myself. I treat myself into what I say.